Okay, well, thank you for the opportunity to present here. I was presenting this yesterday and there were some technical glitches. So what I'll do is I'll move through some of the introductory material fairly quickly for those that might have seen it already. And I think the slides will be made available anyway. And I'm happy to receive any questions afterwards. So I'll move through that very quickly and then just concentrate on some of our sample projects that are relevant to wireless communications and adjacent technologies to support command control and communications. So yeah, just briefly, we're an industry-facing research group at the University of Canterbury with expertise spanning both wireless communications and geospatial technology, and that combination proves to be very useful. We have a bunch of industry partners and projects I've worked on over the years. So I'm just going to skip through this. So our bread and butter, where we started, was really mission critical communications, particularly with our customers Tate and their sister company Mimamax, both in the area of public safety and for utilities, so sort of professional Internet of Things, if you like. And what we're seeing here is big changes in this industry as we move from voice-centric solutions on narrowband radio systems to incorporate data, and from traditional all-informed means of communication to a need to somehow filter the data and make sure the appropriate data gets to the appropriate users and not overwhelm people in order to enhance situational awareness and not bamboozle. And furthermore, we're seeing a convergence of technologies away from specific standards for the public safety community, where they're also adopting consumer level standards, 3G, 4G, 5G. But in fact, the frontline workers don't really care what's behind the button. They just want to push the button and it works. So we have these heterogeneous radio solutions with a combination of traditional radio along with more consumer level radio, but working through sort of user interfaces that professional users are accustomed to. I've just been told that my video is off. However, as far as I can see, my video is on, so I'm not sure that I can do anything about that. I think you can cope without seeing my face, as long as you can see the slides. So I'll just press on rather than try and diagnose that problem. Okay, so I've already touched upon some of the stuff we do on our utilities also. Connected and autonomous vehicles, again, I talked about this briefly yesterday, so I only just touch upon it here. So in the connected autonomous vehicle space, or the intelligent transportation systems space, to give its other common name, we strongly believe that the connected aspect is important, so that the coordination between vehicles and roadside objects, traffic lights or even pedestrians, that adds a whole extra level of capability beyond trying to make the vehicle completely self-contained autonomous without the need to be connected. The catch is there's a bit of a war of standards in this space, with sort of bespoke standards, the WAVE or the DSRC, which comes out of the IEEE world, to give it its number, 802.11p, and evolutions from that. And the cellular world, where V2X, cellular V2X, is being added into 5G systems. And that hasn't kind of settled down. In fact, in New Zealand, we don't have a spectrum allocation yet defined for the dedicated ITS standard. And so there's still a bit of a shake-up in here. And we're getting involved in projects which are comparing these two different technologies and specifically taking them into spaces where traditionally they really haven't been designed for, and warehouse logistics being a very important one, where, for example, fork trucks running up and down aisles in warehouses. Now, the couple of challenges there. We don't have GPS inside a warehouse, so we need a positioning technology. We can use wireless technologies to assist with positioning. And also, it's a very cluttered radio environment. So we're doing a lot of work on characterizing that radio environment. What you see on the screen now are some pictures from some early measurements we took using some DSRC equipment provided by Coda Wireless, who are at the forefront of this area. They've lent us some equipment here. And we're using a corridor in our mech-eng wing here as a proxy for something like a warehouse aisle. Actually, it's very weak. We're in a real warehouse taking measurements there. The cluttered environment, particularly the number of metal objects around, it provides particular challenges for these standards to work with the reliability required so that you can build autonomous systems and be confident that they're not going to, for example, have fork trucks run over people or fork trucks crash into each other. So that's a work in progress. I'll now slow down a little bit because I'm going into material that I didn't get a chance to present yesterday when the technology sort of failed on us. 5G and 6G systems. Now, in the quest for more spectrum, you know, we have this appetite to send more and more data, connect more and more things, more and more people. So we're running out of spectrum for our traditional standards. So 5G moves to higher frequencies, so-called millimeter wave frequencies up in the gigahertz or tens of gigahertz range. And 6G, although not defined yet, the discussions about 6G are really just getting underway. They're envisaged to go up into the terahertz band. So that's 300 gigahertz plus, where we're talking about wavelengths less than 1 millimeter. Now, that's a double-edged sword. With smaller wavelengths, we have smaller features, and hence we can pack antennas much more closely together. So, for example, on the right-hand side here, we have a Nokia 5G base station with 64 antenna elements. That's around about, eyeballed it at about half a square meter, give or take. So, and I think I calculated those, the wavelengths is about 11 centimeters or so. And so those antennas are spaced at around about 3/4 of a wavelength. And so the signals you get into each antenna are reasonably decorrelated, so you can use this to for a bunch of different ways. There's a multitude of ways you can use multiple antennas, but if you were doing it for spatial multiplexing in order to increase data rate, then having this decorrelated signals coming into your antenna elements allows you to, in principle, get up to a 64-fold improvement in capacity. Although in practice, you're not going to try to use it for simply capacity improvement, because the other side of that double-edged sword is that at these higher frequencies, you get a lot of attenuation. So you need to be much more careful about directing the energy, focusing the energy on the areas where you want it, because you have a finite energy budget. So you want to point it where you need to receive it. You need to effectively increase your link budget by using some beamforming technology. So there's a combination of spatial multiplexing and beamforming. Point being that you're moving to more and more antennas. In fact, in the 6G world, we're envisaging ultramassive MIMO, where we might have arrays of 1,000 or more antenna elements. And so that gets pretty scary from a signal processing point of view. But how do we take advantage of such massive arrays of antennas? Doing what we do with current systems that have 4 or 16 antennas would become very, very expensive if we just tried to put a fully digital pre-coding step behind every RF chain. We can't afford to do that. So I don't want to get into too much about the details of this particular configuration, but what we're looking at here is a hybrid beamforming approach where we have a number of data streams to send to K users. So I have, say, K data streams to go to K users, but we have a much, much larger array of antennas. And so what we can do is use a small precoder, this digital baseband precoder, which is of the order of size K, and then use a smaller number, or use only K RF chains, but we have this very large analog RF precoder, which is labeled here as a block F. and that converts our K streams into the very large numbers of antennas. Potentially, you know, K might be, say, 16 users, or we might have 1,000 antennas. So by using this analog block, we're avoiding having to have a digital precoder of magnitude of the order of 1,000. We keep that down to a magnitude of say 16, the number of users here, but we can still take advantage of the very large antenna array we have. And some recent work, I quote it down in the second major bullet point there from 2016, and some follow-up work after that showed that if you have the number of RF chains greater than or equal to 2 times the number of data streams, then you can get optimal capacity out of this system. So you actually do not need a digital precoder to extract the maximum capacity out of the system. So and furthermore, if you trim that back a little bit, you don't go to 2 times the data stream, but you go for something a little bit less than that. There's a bit of a trade-off, and you can closely approach that full capacity. So that's great. That gives us some tools to design these systems as huge numbers of antenna elements at these very high frequencies and get maximum capacity out of them. What we're quite interested in, though, is spatially correlated channels, because when we start getting these high levels of attenuation and also poor reflectivity of surfaces at these higher frequencies, it means that we get highly spatially correlated channels. We don't get signals bouncing around and coming into our receiver from a wide angular spread. We tend to get signals coming from pretty much the same direction, and we get correlated channels, which means that we decrease the capacity of our system. So what we've been exploring is nonlinear precoding. And again, I don't want to go into too much detail here. This is just an example of some of our capability to innovate new solutions and to build sophisticated simulation models and extract performance metrics out of systems. And so here we have all the dashed lines are traditional systems. The solid lines are using this nonlinear precoding method, and the different sets of curves are for different angular separation. So the blue curves are where we have a broad angular separation of paths impinging upon a receiver. So that would be an uncorrelated channel. And you can see that there's not much difference between the traditional system and our nonlinear system, a nonlinear hybrid precoding system. As the channels become more focused, more narrow angular spread, we see that the gain goes up. In fact, we get 5 dB gain when we have a ½ degree angular spread. So very interesting results. Watch this space. We're still working in this area, and it's very exciting for, we will need techniques like this in order to make those very high frequencies and those very large antenna arrays to work in practice. Okay. Moving on, software-defined radio. We do a lot of work with software-defined radio. They're a very convenient platform on which we can prototype wireless signal processing solutions. So we've done some work. In fact, we've done some work with the Defence Technology Agency on using software-defined radios for covert military communications with low probability of detection or interception. I can't tell you much more about that, but we did successfully demonstrate links using some of these universal software radio peripheral devices, USRPs. We've used it for animal tracking from drones in subantarctic waters on islands well south of New Zealand. And we've also used it for software-defined, the platform on the left, which is a little bit more of a bespoke platform, but still nevertheless programmable in that a lot of the processing is done in software rather than in hardware, so giving us much more flexibility. And that was to build a maritime AIS, automatic identification system, and to make AIS feasible for much smaller craft than what they're traditionally used for. Yeah, so we're talking ships here around ports. And adding AIS into leisure craft. So that was quite an interesting project. One of our other key interests is drones, UAVs, unmanned aerial vehicles, and particularly because drones become quite ubiquitous, drone swarming. So what you can do when you have multiple drones. And so we have a lab which extends across 4 departments in the College of Engineering, and we have 9 multi-rotor reconfigurable drones with the high levels, lots of sensors and lots of onboard processing. And then we have numerous bespoke platforms. Our main fleet is provided by Aeronavics, a New Zealand-based company out of Raglan. So really good use of drones is to remove people from dangerous places. So to send a drone in rather than send people in. So we had a project funded by the Royal Society of New Zealand and working collaboratively with Yokohama National University in Japan, focused on search and rescue. We'd had earthquakes in Christchurch, they'd had the tsunami, so massive areas with numerous casualties. So the concept here was that these days everyone is carrying gadgets that have wireless on them. So be they smart watches or cell phones, we put out a wireless signature. And the idea is that we could fly a drone or a swarm of drones over a very large area to conduct search and rescue, and also do some form of triage and get signs of life from these various body-worn sensors. So the picture there is sort of a mock-up whereby you might have identified a couple of people in those buildings which are basically doing okay, you rescue them later. A couple of people that are in red because perhaps they've deceased already, so again, you might leave them later. And perhaps a casualty in that car there which needs more immediate attention. It assists in that triage, that search and rescue and triage, without having to have people climbing over rubble and putting themselves at risk. So we've done this project in multiple phases. We've looked at the radio detection phase, the flight planning phase for a single agent, and some of the drone swarm coordination, the multi-agent stuff. But this is still an ongoing project. Another obviously very dangerous area for humans to be is around volcanoes. So we've done some prototype of using drones to sample both air and okay, I can't play the video here, but where a drone will be towed up on effectively a weather balloon through an ash cloud and then released and take a bunch of samples and then fly back to the ground where the samples can be retrieved and the data that's collected can be retrieved. Also, where a drone can carry a device into a volcano and actually physically collect samples and bring those samples out. Again, a good use of a machine rather than a person. Okay, Antarctica. Being the University of Canterbury, we have a very strong program in Antarctica. And so we're looking at using drone swarms to help scientists understand the ice volume in Antarctica and hence the progress of climate change. So the challenge here is you have to measure both the bottom and the top of the sea ice. So you've got to measure the ice-water interface and the snow-sea ice interface. And traditionally, that's either been done with a big drill, which you saw in that last slide, or with this what's called an EM bird towed under an aircraft such as a helicopter or an aircraft. Big and bulky and expensive and involves numerous people. So we are trying to shrink some of these instruments down and integrate these instruments onto things into a size that can be flown on a drone. So here's our 8-rotor drone, and ultimately can be flown autonomously across large areas of Antarctica to collect a whole lot of data rather than just taking point samples, with the traditional manual approach or the expense of using aircraft, which you can only do infrequently. So the idea is that we'd be able to survey larger areas autonomously, more cheaply, and hence more frequently, so get much more of a temporal map as well as a spatial map. So yeah, here's a little video which just shows some test flights in Antarctica of the snow radar system. And this is the data we get back. So it's a bit like a ground penetrating radar. You get echoes back, and if you're expert at interpreting these things, you can then infer the thickness of the ice from such measurements. Okay, drones can also be used for provisioning communication networks. So for example, back to the Antarctic project, we've looked at using multiple drones for doing the measurements, relaying back to a ship via a one drone which contains a relay. So that extends your operational range, and the measurements have to be taken quite close to the sea ice. So the worker drones, let's say, have to be quite low altitude, which limits their propagation, their range. Hence, we have this intermediate node, which is able to handle the telemetry and the data communication between the worker and the ground station on the ship. We can also use it for, and this is a conceptual diagram, not a real working system, but we can use it to build networks in the sky. And we particularly looked at the capability to do joint beamforming across multiple nodes in the sky. You know, I showed you antenna arrays before, which are fixed antenna arrays, and the elements are all mounted on the one substrate and hence have to be reasonably close together. And we talked about the fact that we might lose some loss in independence between the signals, some correlation between the received signal because of the proximity of those antennas. Well, what about if we could spread those antenna elements out across the sky? And furthermore, how about if we could optimize their position just by nudging each antenna element, you know, a quarter of a wavelength to the right or the left in order to optimize the capacity? And yeah, well, I won't go into the details, but we did find that nudging was effective with some caveats. Nudging gave about the same advantage as beamforming by itself, and we were hoping when you add them together, you'd get a combined advantage, which is about the sum of the two different advantages. Unfortunately, we only got a marginal advantage. So, but nevertheless, it's an interesting approach that you can try to enhance your system capacity by moving your antenna elements, if your antenna elements are actually mounted on autonomous remote nodes such as UAVs. Okay, another interesting and you know, quite out there project when it was brought to us as a proposal was to use drone swarms to track insects, essentially, and this is a biosecurity application, but in fact this can be generalized to tracking any small object, particularly where you don't want to use a powerful transmitter which has a battery on it. So we're talking about insects here that we can't put batteries on. So we use something called a harmonic radar. Now, harmonic radar tag, which is what you put on the insect, doesn't require a battery, and hence you can make it really, really small. And effectively what it does is double the frequency, which gets around the radar clutter problem. The traditional problem with radar, if you point it down towards the Earth, is that everything reflects back. So you put out signals from this blue transmitting antenna here at frequency f sub 0, and you get reflections back into your receiving antenna, the red one in this diagram, from every object at f sub 0. But you tag this very small object, in our case an insect, with one of these harmonic radar tags, and it doubles the frequency, and it's the only thing in the environment that has this nonlinear response, and so it's responding at frequency 2f. So hence you can, at your receiver, you can filter out everything coming back at f0, and the only object you see in the environment is the thing that you've tagged with this very small harmonic radar tag. It's the same principle being used by Reco for avalanche beacons, which you might see built into ski clothing, for example, except we have to make it much, much smaller. And so we've built these tags. We're not the first to have built them, but we've come up with a more reliable way to build them in a repeatable manner. So you can see the top diagram, this is someone else's work, where they used it to track bees, but this particular construction approach, one, was too heavy for us, and two, was not very repeatable. Every tag you built had a different frequency response. The lower approach is how we built it and put it on our target insect there. And so by putting the diode, which is a non-linear element that creates this harmonic response, and the inductive loop on a little substrate, that meant that every tag we built had effectively the same response. And so this is also an ongoing project. We've built receivers, again, using software-defined radios, very flexible radio platforms, and we've achieved a tag weight of 20 milligrams at a range of 14 meters. Now, our target is actually sub 10 milligrams, so I still have a bit of work to halve that weight, and would also like to get a range about double that so that we can follow insect at about 20 or 30 meters away, because at 14 meters, we're concerned that the behaviour of our UAV may interrupt the behaviour of the. All right. So yeah, that tagging principle we're using insects can be used for anything where you don't want a large tag and power-hungry tag. I'll just say we've done numerous studies over the years for the Defence Technology Agency on, for example, satellite comms and. But I won't go into that because it's a lot of that's confidential. So yeah, if anyone has any questions, you can follow up on that email address. Thank you very much.